Hello and welcome to the section on dot product. We want to start by going to the board and working a couple of problems that involve finding the dot product of two vectors. Here's our first problem. We want to find the dot product of this vector 6, 6 with this vector 3, 5. Now you know if this is written in component form it would be 6i plus 6j, and this vector in component form would be 3i plus 5j. You also know from reading the book that to find the dot product of these two vectors we simply multiply their horizontal components. 6 times 3 is 18. Add that to what we get when we multiply their vertical components. 6 times 5 is 30. And so that gives us a dot product of 48. Now, as you know from reading the book, the dot product is a scalar product, not a vector product. So whenever I take two vectors like this and find their dot product, I end up with a scalar, in this case 48. Let's take a look at our next problem. For our next problem, I want to find the dot product of u and v, where u is I plus j and v is I minus j. Now you want to remember here, when you don't see these coefficients, this coefficient is 1, so is this one. This coefficient is 1, and this coefficient is minus 1. So in this case, u dot v again will be the product of the horizontal components. 1 times 1 is 1, plus the product of the vertical components. Plus 1 times negative 1 is going to end up to be negative 1, and that comes out to be 0. So I have negative 1 plus 1 is equal to 0, and whenever my dot product comes out to be 0, that implies that the vectors u and v are perpendicular. So in this case, my vectors are given in component form like this. So again, I still use my same rule, and that is to multiply the horizontal components, add that to what I get when I multiply the vertical components. In this case, that dot product comes out to be 0, and I know from the work I've done in the book that that means that these two vectors are perpendicular. Let's take a look at another problem. For our next problem, we want to find theta between the vector u equal 13i and the vector v equal minus 6j. So I'm going to write this first vector as 13i plus 0j, just to remind us that even if I don't see that vertical component, it's really there, it's a 0. And then this vector I'll write as 0i minus 6j. Now I know from reading the book that the angle between these two vectors is given this way. Cosine theta will be the dot product of u and v divided by the magnitude of u times the magnitude of v. Well, the dot product is easy to find. I'll just multiply my horizontal components and multiply my vertical components. You see I have 13 times 0, which is 0, plus 0 times negative 6, which is 0, so I end up with 0. Now, if I was to write down the magnitude of u, I would have the square root of 13 squared plus 0 squared. That would end up to be just 13. And the magnitude of v would be 0 squared plus negative 6 squared, the square root of all that. That would come out to be 6. But in this case, it really doesn't make any difference because my numerator is 0, meaning that that whole cosine theta is equal to 0. So if cosine theta is equal to 0, that implies that theta itself must be 90 degrees. So again, when the dot product here ended up to be 0, that gave me a cosine theta of 0, and that tells me that the angle between those two vectors happens to be 90 degrees. Let's take a look at another problem. For this problem, we want to show that the vector v equal ai plus bj and the vector w equal negative bi plus aj are always perpendicular. Well, let's find the dot product of these two vectors. V dot w is going to be equal to, well, I'll multiply my horizontal components, a times negative b, and I'll add that to what I get when I multiply my vertical components, b times a. And so I have a times negative b, which is negative AB plus B times A, which I can write as AB. And so I end up with just 0, which implies that V dot W, which implies that V and W are perpendicular. So anytime my dot product comes out to be 0, I know that I have two perpendicular vectors. And if I happen to have two perpendicular vectors, I know that their dot product will always come out to be 0. Let's look at another problem. For problem 5, we have a force F, which is equal to 22I plus 9J, is applied to an object, displacing the object according to the vector D equal 30I plus 4J. Find the amount of work done. Well, you know from reading the book that if I take the dot product of these two vectors, I'll end up with the work. Now we're going to assume that force is given in pounds and distance is given in feet. So a force represented by this vector is applied to an object and it displaces the object this many feet according to this vector. Well, from reading the book we know that the dot product of force with distance is going to give us work. So work is going to be the dot product of force with distance. So that dot product is going to be, again, the product of the horizontal components, 22 times 30, plus the product of the vertical components, 9 times 4. Okay, and that ends up to be, let's see, I think 660 when I multiply these. 660 plus 36, and that will come out to be 696 foot-pounds. So 696 foot-pounds, that is the amount of work that's done when I apply this force to an object and displace the object according to this vector right here. So work, and one way to write work is as the product of force with, as the dot product of force with distance. Let's take a look at one more problem. A package is pushed across a floor for 75 feet by a force of 15 pounds at a downward angle of 20 degrees from horizontal. Find the work done. So I've drawn a little picture of this right here, and it shows that here's the object that's been moved. Let's say we have a little object right here, a package, and it's been moved 75 feet, okay, in the horizontal direction. So the magnitude of this vector is 75, and its direction is exactly along the horizontal, by a force that's applied to it in a downward direction 20 degrees from the horizontal of 15 pounds. So what's the work done in moving this object from here to here with this force? Well, if you read the book, you'll see that the amount of work done is going to be equal to, there's a couple ways to write this formula. We could take the dot product of these two vectors, which would involve writing this vector in terms of its horizontal and vertical components, but we can also use a second formula that's in the book, which says that the work done is the magnitude of the vector F times the magnitude of the vector D times the cosine of the angle between them. Well, if I have this formula, the magnitude of F is just 15, the magnitude of D is 75, and I have the angle between them, which is 20 degrees. So using this formula, I find a very easy way to find the amount of work done in moving this package from here to here with this force. So it turns out to be the magnitude of F, which is 15, times the magnitude of D, which is 75, times the cosine of 20 degrees. Now if I do that calculation on my calculator and round off to 2 significant digits, I get 2,800 foot-pounds. Now I rounded this off to 2 significant digits right here because that's the accuracy I have in with the numbers that are given in the problem. I have 2-digit accuracy, so I'm going to go down here with significant figures and round this off to 2,800 foot-pounds. But some problems are easier to do using the dot product. Other problems are easier to use using this formula, and certainly a problem that's written like this would be the simplest way to do it. Magnitude of F times the magnitude of D times the cosine of the angle between them. It's a simple multiplication problem. I do this on the calculator, 2,800 foot-pounds. So there's a look at some dot products involving the vectors.